Okay, some of you were at Hebden Bridge when I presented this in early September. Forgive me if you've seen some of this content. I've reduced it, and it's about 17 seconds a slide. So we'll just whiz through it. Who knows this book? Okay, who's followed the course? Okay. Commonly known as From NAND to Tetris. It was written about 10 years ago. It is basically creating a 16-bit computer from first principles. The first 5 chapters of the book are the hardware, and it introduces combinational and sequential digital logic. It introduces the concepts of the ALU, the program counter, registers, memory interfaces. And in 5 chapters, you design the chips using basically a simulation that will run on any PC platform. And once you've created about 12 or maybe 13 chips, you stitch them together and you have at least a simulation of a working 16-bit processor. Now, I did this a couple of years ago, and although I've been in hardware for 30 years, when I got that 16-bit simulation to work, I had the aha moment. That's how it works. Anyway, then we get to part 2 of the book, which is the software. And you start with machine code, and then you write an assembler, and then the concept of the virtual machine is introduced, and then high-level languages and compilers and blah-de-blah. Anyway, I got a bit lost in that section. So clearly I need to go back to school. So how are we going to prepare the next generation of engineers, and I'm talking computing science and electronic engineers, how are we going to prepare them for this new industrial revolution that we're going through? Okay, so, blow my own trumpet. This little device is something that I have had in the back of my mind ever since I did the NAND Tetris course. And I thought, if only we had some real hardware. So when Alan and I got together at the end of May, I was very supportive, and together we created this in 100 days. And this is real hardware that you can now develop your own processor architectures on. But you can also do a lot more on it. Okay, heroes of computing. When I was going through college 30 years ago, I suppose we had heroes like Jobs and Wozniak, because they were the heroes of the 8-bit generation. And I didn't really know anything about any of these guys whatsoever. They should be very familiar to most of you. But the one thing that they had in common is that they were all totally pissed off with the state of the tool chains that they had. And this is a recurring theme. So they got on and they wrote their own. Okay, anyway, going back to what can we do to improve education? Well, we've got new platforms available. We've got a host of single board computers, incredibly powerful devices that only 5 or 10 years ago we couldn't even imagine having such low-cost computing platforms. And the advent of these low-cost computers mean that we can have new open-source design tools. I'm talking things like KiCad for designing PCBs. If we had a suite of engineering tools that would allow undergraduates to basically design both in hardware and in mechanical and code, Verilog and VHDL, but an integrated tool set. So that's something to think about. Okay, and then we've got new manufacturing technologies. We've got 3D printing, we've got laser cutting, we've got plasma cutting. One example is the little acrylic case that we supply with MyStorm. That was knocked up in a couple of days by Andrew, who's sitting at the back somewhere. Thank you, Andrew. So we've got new ways of doing things, and we need to buy into that the world is a changed place, and we need to get a grip and find ways of making this stuff work well for us. Okay, there's an example of a single board computer, quite a good one, the Odroid, rather quick. Okay, so what can we do for ourselves, DIY? If you were to give an engineering student a platform at the start of the first term that they can run a course similar to NAND Tetris on, and they can learn right from scratch the elements of modern computing systems. And they can use this, and they can take it back to their study room, put it in the backpack, take it home. They can experiment wherever they are, on the train, on the bus, whatever. So you've got this personal lab in a box, basically, that you can experiment with. And then you can learn by doing. Students of electronic engineering, they can create their own tools, digital storage oscilloscopes, logic analyzers, digital voltmeters. There's a whole host of things that are very simple to do with this sort of technology. Okay, here is something that National Instruments do for about $150. We need to make an open version of that for $20 and publish it on the web. Okay, PyTop, a do-it-yourself laptop based on a Raspberry Pi. There's a spare slot in the middle into which, quite conveniently, you could put a MyStorm if you wish. Okay, we've got new chip architectures that we've heard about this weekend. But there's some others that I've put up there. Who's heard of Oberon? Yeah? Okay, you can implement it on a Spartan 6. Niklaus Wirth, obviously, creator of Pascal, Modular 2, and gone on to try and simplify. He doesn't like 20 million lines of code. I think Oberon fits into about 100,000 lines or something. Charles Moore, founder of the Forth language, he's now working on arrays of Forth computers, Parallella. And you might not know Jeff Fox. Sadly, Jeff died in 2010, but he ran a little company called Ultra Technology. Google it. And 20 years ago, he and Charles Moore were working on some extraordinary stack-based architectures. Please have a look if you've got some spare time. Okay, new languages. Yes, you're probably familiar with all of these. MyHDL and Lola, you may have come across those. Lola is Niklaus Wirth's Oberon-based language that produces a Verilog, which can then be compiled in the usual way. Okay, new ideas on tools. I learnt about a very fast electron beam lithography machine from a colleague this weekend. We can print chips, and we can rapid prototype chips. Okay, we're potentially going to have open FPGAs sometime soon. The emergence of open source design tools. And we need to simplify and demystify the whole process of digital design and chip design. And we need to teach IC design to undergrads. And where's our friend from Columbia? Is he here today? Well, I think he's already started that. Okay, so getting started on this. NAND Tetris is one approach. There's a proliferation of open platforms, low-cost SBCs, affordable hardware. We need a collaborative effort to produce easily accessible, well-researched teaching content. A product is no good unless it's got content. And then we need to build communities and ecosystems around these new ideas, these new products. in at the deep end. I had a young Vietnamese lad come and join me for a year as an industrial placement. He was very shy, didn't speak a lot of English, but in a year, I had him laying out multi-layer boards and soldering, and anyway. Right, teach a man to fish, and finally, we need to improve the standard of our technical education so we stand out in a crowd. Okay, thank you.